morning, student. We'll start with our today's lecture. So basically in the last lecture we had completed deadlock modeling, that is how a resource holds a process, that is how resource has been allocated to a process. If a process is request for a resource, how it is being shown, and how a cyclic graph can occur, a circular weight condition can occur, because of which deadlock situations take place, that we had seen. So in today's lecture we'll be seeing the deadlock modeling and what are the conditions for deadlock modeling. So a request R, a request S, a release R, a release S. So with these, request S, request T, release S, release T, once there is request and release, this problem can be handled. But when there is request and it is requested by some another resource process also, then there can be a conditions for deadlock. So these are the examples why deadlock can occur. Next is, this is the condition where deadlock occurs, that is A has R and has requested S, B has S and has requested nothing, but until and unless B releases S, A will not get completed, because of which where C is also requesting, what can happen? So we can have these solution. These are the solutions by which we can avoid the problem of deadlock. The first is, what we can do is, first we can, if A has R, A is requesting S. If A has S, once A releases S, we can, B releases S, it will demand for T. If C releases T, it will get R. So this is here what the condition is, that A has R. Once A completes the work with R, A will request S. Once B releases S, B will request T. Once C releases T, it will get R. That is, interdependencies of these release and request resources can avoid a problem of deadlock. So these are the examples how we can have no deadlock conditions. Even if we go for one single resource at every time, this problem can be solved. Next is a deadlock modeling and how it can be avoided. The last one, that is when R is released by A here, and when it gets S, we can give it to C so that it releases, it completes its work, that is R with R and T, C process completes its work. So this can be a condition, that is providing both the resource. Now it is not compulsory that every time you will have only one resource requirement, you can have more than one resource requirement also for completing the process. So what are the strategies? So they have said that deadlock modeling, when we design deadlock or when deadlock occurs, what are the strategies which can be taken to avoid deadlock? The very first is, we will read strategies used for dealing with deadlocks are, first one is, ignore the problem, maybe it will go away. So what we say, sometimes a system is getting shut down frequently, what we can do is, we can avoid the problem, it will solve the problem internally, we will not see into it. Next is detection and recovery. Let deadlocks occur, detect them and take actions. So next step, what we can do is, we can wait, we can check that yes, this problem is occurring, let the deadlock occur, we will detect in this particular part it is getting a problem, and then we will take the necessary actions to solve it. Third is dynamic avoidance by careful resource allocation. What we can do is, we can have a check over the resource allocation processes, so that we can have a dynamic avoidance somewhere, dynamically providing, that is new creation resources providing according to the demands of process, so that deadlock can be avoided. Next is prevention by structurally negating one of the four required conditions. So as I had explained you in the last lecture, that there are four conditions by which a deadlock occurs, and because of which, even if one of those conditions does not satisfy, so what will deadlock will never occur. It's a never ending condition then. And for that, what are the four conditions? Mutual exclusion, no preemption, hold and wait condition, and circular wait condition. So through which, if I say hold and wait condition never occurs, if we remove that condition, deadlock will not occur. So what are the four deadlock modeling strategies by which we can avoid deadlock? Ignore the problem, maybe it will go away. Second is detection and recovery. Third one is dynamic avoidance by careful resource allocation, and fourth one is prevention by structurally negating one of the four conditions of the deadlock. So when we are talking about deadlock detection, so what is deadlock detection? If the system does not make use of deadlock prevention or deadlock detection algorithm, then the system will observe the deadlock situation. So if system is not looking towards the deadlock prevention and detection algorithms, it does not has, then deadlock situations will occur. And in this situation, it is necessary that system should have what all system should have to detect those deadlock. First and very foremost, algorithm which examines the deadlock system has deadlock occurred the deadlock or not. To check, you should have an algorithm. Second, you should have algorithm to recover from that deadlock if it is occurred. If deadlock has occurred, we should have a algorithm to recover it. Next is both the algorithm requires overhead, so they require an overhead including the runtime cost of maintenance. So these require a runtime cost maintenance, then necessary information and executing the detection algorithm, and the potential losses are natural in recovering from deadlock. So financial losses, or we can say the natural losses of the data, can be a reason for these deadlocks. So the first type of deadlock detection is with one type of resource each. So when we talk about only one resource for one process, what is the scenario? We'll see that a deadlock detection algorithm make use of wait for graph, which is resource allocation graph. So example of a system, if is it deadlock, so what they have given here: process A holds R, wants S; process B holds nothing, wants T; process C holds nothing, wants S; process D holds U, wants S and T; process E holds T, wants V; process F holds W and wants S; process G holds V and wants U. So we'll go with this diagram. Process A holds R and wants S. Process B holds nothing and wants T. Process C holds nothing, wants S. Process D holds U and wants S and T. Process E holds T and wants V. Process F holds W and wants S. Process G holds V and wants U. So here, as you can say, these all statements I have explained with this diagram. Means what? The arrow which is going from a resource to process is actually holded by that process, and the arrow which is going from a process to a resource is requested a resource from for that process to get completed. So this was a correct diagrammatic representation of one type of resource each, that is each one is having one resource which is holded and wants another resource to complete its task. In that resource graph, one part which is there is a cyclic graph which is being dependent. If D wants T but B is not releasing T, if even B and D wants T, but E is not releasing T. Why? Because it wants V, which is being holded by G. G is wanting U, but it is actually holded by D. So there is all the conditions. Until and unless D releases U, these tasks will not be completed, and until and unless, because D will not release U and D also wants T, which is holded. So interdependency and a cyclic condition is being occurred, and because of which deadlock can occur, which is being shown. This is just an one part which is being removed to show where deadlock condition can occur with the dependencies, which is being explained in this whole process, or we can say in the deadlock detection algorithm. So what is the algorithm? I'll just read it out. No hard and fast rule, we are not using this algorithm anywhere, but for your like explanation, I have been put these steps. For each node n in the graph, perform the following 5 steps in n as a starting node. Initialize L to empty list and designate all arcs are as unmarked. So all the arcs will keep unmarked. Add current node to end of L and check to see if node now appears in L 2 times. If so, graph contains a cycle and algorithm terminates. So what we had done here also, in the if they have two nodes, it will terminate because there is a sharing, that is from here we have cut down, and here there is no extra endpoint. So we have cut it down here and we have taken this as part for the circular wait condition. From given node, see if there are unmarked outgoing arcs. If so, go to step 5. If not, go to step 6. We will previously again repeat the same steps. If not, we'll continue with the further steps. If this initial node graph does not contain cycle, algorithm terminates. So if there is no cyclic graph anywhere, what it will do? It will discard the process and remove the process. Next type in deadlock, first one was with one resource of each type. Next is multiple resources of each type. So when we talk about multiple resources, the wait for a graph discussed above is not applicable to multiple instances. So the graph which we had drawn prior for one resource of each type is not applicable here for multiple resources. Multiple resources, in this case we have to use detection algorithm similar to Banker's algorithm. So similar to your Banker's algorithm, your multiple resources type graph is there, or we can draw the graph like that, and for that you have values a of m, that is array of the resources, the values of the resources. Second one is c of n into m, that is current allocation matrix, and request matrix, that is R, which is denoted by R, be two dimensional. R can be R into ij, that is this multiplied by this. So the 4 data structures needed. So there can be multi-level matrix here which can be defined. With this, we'll stop here for this lecture. We'll continue the next topic in the next lecture. Thank you.